Time is the most familiar, yet the most mysterious aspect of our existence. From the rhythmic ticking of a clock to the inevitable aging of stars, we are swept along by a current that seems to flow in only one direction, the future. This is the arrow of time. However, when we peer into the fundamental equations of physics, from Newton's laws to Schrödinger's equation, we find a startling symmetry. These laws work just as well in reverse. If you were to watch a movie of a subatomic particle interaction, you couldn't tell if it was playing forward or backward. Yet in our macroscopic world, an egg, once broken, never spontaneously reassembles. This discrepancy between the micro world of symmetry and the macro world of directionality is one of the greatest paradoxes in science. To solve it, we must look beyond our sensory experience and into the heart of quantum gravity, guided by the provocative philosophy of mathematical realism, which posits that the universe is not just described by math, but is fundamentally composed of it.
For over a century, physics has been a house divided. On one side stands General Relativity, Einstein's masterpiece, which describes space and time as a smooth, continuous fabric warped by mass and energy. On the other side is quantum mechanics, the bizarre and probabilistic world of the very small, where nothing is certain and everything is quantized. Both theories are incredibly successful within their own domains, yet they are mathematically incompatible. General relativity treats time as a dimension woven into the geometry of the universe, while quantum mechanics treats it as an external background clock. This incompatibility is the catalyst for the search for quantum gravity. If we are to understand the arrow of time, we must first find a single mathematical framework that can bridge this rift. We are forced to ask, is space-time a continuous canvas, or is it made of discrete pixels? The answer lies in the deep structure of mathematical realism, where the logic of numbers dictates the physics of reality. The primary suspect in the mystery of time's arrow is entropy, governed by the Second Law of Thermodynamics. This law states that in any isolated system, disorder, or entropy, tends to increase over time. Think of it as the transition from a highly organized state to a chaotic one. While the fundamental laws of motion are reversible, the collective behavior of trillions of atoms is not. This gives us the thermodynamic arrow of time. But why did the universe begin in such a state of low entropy to begin with? This leads us to the past hypothesis, the idea that the Big Bang was an incredibly ordered state. But the why remains elusive. By applying mathematical realism, we move away from seeing entropy as a mere physical occurrence and start seeing it as a logical necessity within a specific mathematical structure. In this view, the arrow of time isn't an added feature of the universe. It is a property that emerges from the very geometry of the initial conditions defined by mathematical logic.
Mathematical realism, or Platonism, suggests that mathematical entities exist independently of our minds and the physical world. Proponents like Max Tegmark argue for the mathematical universe hypothesis, claiming that our physical reality is a mathematical structure. If this is true, then the arrow of time must be encoded within the structure itself. In this paradigm, we aren't looking for stuff that moves through time. We are looking at a static, eternal mathematical object, where time is just one of many internal parameters. From this perspective, the past, present, and future all exist simultaneously as part of a complex, multidimensional geometric shape. The flow of time is an illusion created by our perspective as observers embedded within the structure. By studying the properties of these mathematical objects, we can begin to see how the arrow of time is not a force, but a logical consequence of the way information is partitioned and connected within the cosmic equations.
One leading contender for a theory of quantum gravity is loop quantum gravity. This theory suggests that space is not a smooth background, but is instead composed of discrete loops of gravitational field lines woven together. These loops form a spin network, where the edges and nodes define the volume and area of space. In this model, space itself is quantized. There is a smallest possible unit of volume. But what happens to time? In loop quantum gravity, time as we know it disappears at the smallest scales. It is replaced by a spin foam, a four-dimensional version of the spin network. This provides a radical new look at the arrow of time. If space is discrete and mathematical, then time might be an emergent property, much like temperature is an emergent property of moving molecules. The arrow we perceive is the result of the transition between these discrete states of the spin foam, dictated by the combinatorial laws of the underlying mathematical lattice.
In the mid-20th century, physicists John Wheeler and Wheeler-DeWitt attempted to combine general relativity and quantum mechanics into a single equation for the entire universe. The result was the Wheeler-DeWitt equation, but it contained a shocking surprise. It had no time variable. This is known as the problem of time. If the equation that describes the universe is static, why do we experience change? This supports the mathematical realist view that the universe is fundamentally a timeless mathematical object. To reconcile this with our experience, physicists propose that time is relational. We perceive time because we are comparing one part of the static universe to another. The arrow of time emerges from the entanglement between different systems. In this view, time is a measure of the growth of quantum entanglement. As information becomes more distributed throughout the mathematical structure, the clock of the universe ticks forward. We are moving through a landscape of logic where the direction is defined by the density of connections.
Another fascinating approach is causal set theory. This theory posits that spacetime is a collection of discrete events, or atoms of spacetime, which are related by a single rule, causality. In this mathematical framework, the order of events is the most fundamental thing. One event precedes another, not because of a flow of time, but because of the logical structure of the set. Here, the arrow of time is built in by design. It is the inherent directionality of the causal links. Mathematical realism here suggests that the universe is a growing causal set. New events are birthed into existence, adding to the set in a process called stochastic sequential growth. This provides a bridge between the static equations of physics and the dynamic experience of our lives. The arrow is not a mystery here. It is the very definition of how the mathematical set expands. It suggests that the future does not yet exist as a part of the mathematical structure, but is being continuously calculated by the laws of the cosmos.
Black holes serve as the ultimate laboratory for quantum gravity. At the event horizon, the laws of general relativity and quantum mechanics collide in a way that challenges our understanding of time. According to the holographic principle, all the information contained within a volume of space can be described by the information on its boundary. This implies that our three-dimensional reality, including the passage of time, might be a projection of a two-dimensional mathematical code on the edge of the universe. Inside a black hole, the arrow of time might actually swap places with a spatial dimension. As you fall toward the singularity, the center of the black hole becomes your future, an unavoidable moment in time rather than a place in space. By studying these extreme mathematical limits, we realize that time is far more flexible than we thought. It is a derivative property of information density and the way mathematical structures encode the history of the universe's evolution. Ultimately, the study of quantum gravity through the lens of mathematical realism leads us to a profound conclusion. The universe is a coherent, logical, and deeply structured entity. The arrow of time, which once seemed like a cruel reminder of our mortality, is revealed to be the very mechanism through which complexity and life can exist. Without the increase of entropy and the directed flow of time, there would be no processing of information, no evolution, and no consciousness to observe the beauty of the cosmos. Whether we live in a spin foam, a causal set, or a holographic projection, the underlying mathematics ensures that the universe has a story, a beginning, a middle, and a future. As we continue to refine our equations and look deeper into the quantum realm, we are not just discovering the laws of physics, we are uncovering the eternal mathematical truths that give our journey through time its meaning and its direction. The arrow points forward because the logic of reality demands it.